Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also, but there's nobody really engageable in debate. And there's no one to argue all the different little experiments and to argue what they imply and what collectively they almost require as reasonable conclusions regarding function of elements of the universe. Now, a lot of this has to do with the fact that physicists, as a group, tend to think, apparently, that the universe below us, the mechanics of the cells, and then you get down to the atoms, and then the electrons, and then the force itself, that somehow there's features, that it has powers that we don't have. So it can do this in the middle of the air, and they can have ESP, particles can know exactly what somebody else is doing or where it is, and it can react faster than the speed of light. It doesn't, speed of light, speed of force, they don't think it's some sort of basic elemental function that can't be broken, and so they think this small universe has got a bunch of these features that somehow never percolate into the big universe. And it's a lot more complicated, where I would argue that the theory of evolution, different things that have even the way geology works, that the rules get simpler, not more complicated. That the mechanics are just very simple and elemental, and that's going to be the right answer, not some kind of magical pull. For example, push, really easy to figure out how a push could happen. Something bangs into something else. Push, really easy. Pull, not so easy. And instead of concentrating on those glaring facts, I would argue, they, try to bend everything into the more wooey and extraordinary explanation. So nothing is as simple as it could be, and they just keep making things more and more complicated, frankly. So anyway, so this Angela Collier, obnoxious biatch, in the sense, making these stupid videos about crackpots and all this other crap in the context of a physics that is where essentially everybody's a crackpot, until you prove something. So Faraday had all kinds of crackpot theories about gears and idler pulleys and all kinds of stuff inside of materials. I mean, everybody attempting to explain the reality has some theories that just plain suck. And it's just this, certain percentage you get to have their theory elevated to something everybody believes, when there's not all that good a reason to believe any of it. Like many worlds or some other dopey explanation for some experiment that is just glaringly storytelling. It's just, no way to prove it, no way to disprove it. What's the point of it then? I mean, so anyway. So in that context, we'll play this piece of shit video. And it's garbage physics, it's garbage science. She doesn't know how any of this stuff works, and she's pretending she's an authority on something. And she's just an authority on reading the Holy Bible of physics, and that's it. And I don't even know how much of an authority on that she is. So anyway, video starts without any, she doesn't work into it at all.
Thought it would be fun to show you how electricity and magnetism have to be the same force,
So everything's the same force, you could argue. So it's all going the speed of light. It has so many things in common. It's all discrete. It's in little tiny pieces. It's moving very fast. It's all moving the same speed. It's pretty easy to argue that it's all the same force, technically. But clearly, magnetism and electricity are very different phenomena, so we know there's distinctions. So there's no point in saying they're the same thing. They're different manifestations of what might be the same thing. But I would argue that everything in the universe is the same thing. It's just about moving electrons and protons, and that's it. Changing the position of electrons and protons, and when you change their position, you change how it looks. They look different, so when they're in different places, they create a different pattern. So that's all that's happening in the universe, and everything is reacting just the way we do to what it sees. If tigers look like butterflies, well, then we couldn't react and we couldn't jump out of the way or do, not that it'd do you much good. But, it makes a difference how things look, all right? And the universe, the electrons and protons are seeing the universe created by the electrons and protons. All right.
It cannot be two distinct forces.
All right, so, and they're not distinct in the sense that they're the same force that exists in the universe, and all they are is a reflection. So everything sits in the universe, and all it can do is reflect the universe that's hitting it. And if it has electrons and protons, as stated, it can create different patterns of electrons and protons so it can look different. But you're just seeing what it's reflecting. You're just seeing the same thing we're seeing when we say, okay, I see this, it's a 9-volt battery, and I see this different other stuff, that this pair of tweezery things, okay? So these have a different pattern they create. I can recognize the pattern. I can see the pattern because I have the capacity to make these distinctions. Well, yes, the crude matter isn't very smart, so the crude matter can usually only see things as simple as, is it, a bullseye with a blue center and then another, a red line and then a blue line and then a red line, or is it a red center and a blue line and a red line? Is it, it can tell the difference. So things that are polarized can see things that are polarized. Things that aren't polarized can't see polarization. You could argue they can't see the pattern. But that's all it is. Things are just seeing what the rest of the universe is doing, and the light has the power to push them away or push them towards. And it's always a push. It's push away or push towards. And as you do that, as you push things away and you push things towards, you change how the universe looks.
But I also thought it would be fun to try and do.
Yeah, it's all about the fun. Her last video was some stupid physics joke video. I mean, why do people gravitate to this mush physics?
But within 20 minutes.
Whatever.
People have known about electricity for a super long time.
A super long time. It's all super cooly wavy. I mean, all this younger generation stuff. Oh, shit.
The electric fish. You have lightning. People used to collect static electricity, like in jars, to do magic tricks. They called themselves electricians, but it's very charming that they saw, even then, the power of electricity.
So electricity really is the presence or absence of electrons, since that's all you're talking about. Atoms that have a plethora of electrons and atoms that are deficient in electrons. So it's either you're seeing more red or you're seeing more blue, depending on what the volume is of electrons and protons.
What it would do. And then, of course, also with magnetism, people have known about magnetism super long time. You have lodestones that would collect iron filings. People harness the power of the Earth's magnetic field for navigation.
Right, and so the whole point is to point out that this stuff, electricity and this stuff, magnetism, one of them does apparently require you to move particles from one place to another. You have to move the electrons, the charged bits. You have to move matter to create electrical potential. But magnetism, all you have to do is rearrange the existing matter. So I just take a piece of iron, I rearrange the atoms, and when I rearrange the atoms, now they're polarized. Now they're doing this blue thing instead of this red-blue thing. That kind of, you're just basically saying, look, if I shift the material a little bit, I can change what it looks like by just, shifting it.
Compasses. people have known about these things. And then they started getting the idea that, like, maybe these things are related. Let me read you a story. So this is from 1735. A tradesman at Wakefield in Yorkshire, having put up a great number of knives and forks in a large box, and having placed that box in the corner of a...
Right, so this interesting thing about the fact that you can use electricity to cause certain metals to become magnets. You can magnetize them. And you can do it in a lot of different ways, right? You can just put them in a magnetic field and tap on them and they'll become magnetic. So, I mean, there's lots of ways you can cause their atoms to change their orientation. So now they're polarized. Now they're all oriented in the same direction and they're creating a pattern to the universe that other things that are polarized can see.
Large room. There happened a sudden storm of thunder, lightning. The owner emptying the box on the counter where some nails lay. The person who took up the knives that lay on the nails observed the knives took the nails. On this, the whole number was tried, and they found to do the same.
So I guess who's listening to this video where she's going to start talking about relativity, right? The video is basically all of it is mathematics, and then mathematics with gamma, added. Like somehow what frame you're in changes the magnetic field into an electric field or vice versa, which is garbage.
And that to such degree as to take up large nails, packing needles, and other iron things of considerable weight.
I mean, really, people that can handle the math or handle the worst math of even throwing relativity into the argument really don't need to hear this story about, well, somebody, made a compass. They've already known that story.
So here we are. They know that lightning, an electric thing, has caused a magnetism, a magnetic thing.
Right, and we know that basically the argument, the simple argument is that rearrangement can't make it radioactive. It can't make it make a force. So we know it's not making a force. Magnetism isn't a new force in the field. There's no magnetic force being ejected. And the only thing it can possibly be doing is looking different. That is, it's reflecting the universe different than the universe that comes in. The light that comes in comes out a different color, so to speak. And that's all it's doing. And the thing is reacting to whether it's red or blue, like a signal on a street. Okay, green light go, red light stop. And there's always the same light, and all you're really doing is just changing what filter is that the light is going to be produced by. You're just changing the color of the substance, so to speak. I mean, it's a metaphor, but it's a good metaphor in the sense that electrons and protons are constantly seeing each other at the speed of light. That is, the universe is hitting something and it's reflecting something towards them, and they're reacting to the force that's coming towards them.
These things must be related, and it wasn't until James Clerk Maxwell in 1860.
So this way over exaggeration of Maxwell's importance. So she made another video about Faraday, and she was talking about all these scientists in France who died young. And she didn't talk about the fact that, Maxwell was killed quite early, 48, I guess, something like that.
65, who published one of the most brilliant works of physics to say electromagnetism.
Really. I mean, the most brilliant works of physics by your statement. It's just mathematics. He took a bunch of other people's work. He did extensive interviews with Faraday. And just basically put their stuff into a mathematical framework. I mean, not a huge, giant leap in human progress, really. I mean, compared to Faraday's discovery of the functions of magnets, basically making the first motor and stuff, compared to that, I mean, Maxwell's contribution, I would call it minor.
Magnetism. I'm going to take you through an example of why they have to be the same. It's not a proof, it's not a derivation, it's just an example.
Right, it's a silly example using relativity as some sort of talking point. That basically she's saying in one frame the magnetic field is pushing on an electron, and then in some other frame it's the electric field. So in one frame it's the magnetic field, and in the other frame it's the electric field. It's just nonsense. So now she's saying they have to be the same thing, because in one case the electric field is moving it from one frame's perspective, and then from the other frame's perspective somehow it's the magnetic field. Now obviously whatever's moving it is the same. All this stupid frame crap, where you're standing and where you're looking. Yeah, obviously if you're looking at these two from this point of view, okay, you don't see any red, right? I can't tell, but you know what I mean, it's behind it. And if you're looking at it the other way, it's clear, red, blue, no problem. So what? That doesn't mean that this was any different. It just means you have to understand that you have a perspective, and your perspective isn't complete. You're not seeing it from all angles, and from some other angle it could look completely different. That's not a big surprise, but it certainly doesn't mean that when it's this way it's magnetism, when it's this way it's electricity or something. I mean, it's clearly, the patterns are clearly different. Clearly, in both cases it's clearly different, in the sense, again, if I take an atom and it's round, and I say, okay, let me smush it this way, and I push the electrons out this way on the sides. Well, what have I created? Well, I've created two south poles this way and two north poles this way. So I polarized it, but not in the traditional way. It's polarized at 45-degree angles, not at 90-degree angles. Well, not at 180-degree angles. It's polarized at 90 rather than 180. It's understandable. It's not a different thing happening. And you want to model the thing happening, not some point of view specific model, but a model that duplicates the actual functional mechanism. I mean, it's water going through a hose, okay? There's no relativity issue. Okay, obviously the water is moving relative to the hose. There's no doubt about it.
It's not my example. This example is in like every single elementary physics textbook.
Right, so thank you so much. So who needs this? Who needs this video? So she says it's an elementary textbook, and yet she's going to talk about something that's completely not elementary. So what sense does that make? What the hell was that? Oh, it's commercial.
I know my Old Spice Fiji when I smell it.
That's me, Mr. Cole.
Oh.
65, who published one of...
Gross. Yeah, somebody said something about, I told them there was a bunch of, chicks for free kind of ads on video. So now this one's, a free music theory handbook. But yeah, when I see the free chick one, I'll show you the ad. But they also play ads for, get yourself a wife from, some third world shithole.
the most brilliant works of physics to say electromagnetism. I'm going to take you through an example of why they have to be the same. It's not a proof. It's not a derivation. It's just an example. It's not my example. This example is in like every single elementary physics textbook. But it's going to be fun. Okay. So
says you. All right, so I don't even know if this is worth playing any further, right? But she's really not going to talk about anything that happens in the real world. Okay, so I was hoping she'd talk about electricity and magnetism, but she's really not going to, so I guess I will.
So for this problem, let's consider an infinitely long conducting wire.
Why would it matter whether it's infinitely long or not when you're going to put 1 point charge in one place? What the fuck would the infinitely long wire have to do with anything? Oh, that's right, nothing.
It's got some velocity of electrons moving to the right.
Well, then it's obviously got a voltage, okay, higher pressure at one end, and because the other end is infinite, yes, the pressure just keeps going forever, I guess. But there's obviously not some higher pressure at this other end somewhere. So nowhere along the wire is there a high voltage. So it obviously has a lower pressure of electrons. And that's sort of the key point here. So it's just about pressure between electrons.
At speed v, velocity v, I guess, since we know the direction. Inside this wire, you have a flow of electrons moving.
So this is the part that is important because she's going to start talking about this stupid drift velocity. And so the flow of electrons is So this is where they should make their comparisons or try to make analogies, try to add a little bit of context to understanding the mechanism and why we'd even think of it in terms of whatever a wave would be. So, all right, so now I can't say I have all of this nailed down perfectly yet. This was just to illustrate the fact that you could see this two different ways, right? You could look at this red thing and you see that it's a blue ring around it, and then there'd be another blue ring around here. Or you could see it as the blue center with the red ring here and the red, that's the pattern matching part to magnetism. And then this was just to illustrate the difference between the electrons, say, being in front of the proton. That is, they're pushed, they're in balance. They're aggressively pushing against, okay? They have a force pushing, opposing force from the other. Oh, interesting. Oh, boy, that was a mistake, whatever I just did. All right, so there's an opposing force between the electrons and an attracting force. They can't really get closer to the proton without getting too close to the electron. So they're stuck in a position. And then that pressure is equalized in the sense that all the electrons end up feeling the pressure from one electron. So they're all connected to each other. So it's like water molecules or something else that's connected. Electrons are like, when they're in a material, they're equalizing their pressure. So they're all balancing, okay, how much pressure they have. So if one of them's under more pressure pushing, then the other ones push on each other, and it all wants to equalize out in the end. And then obviously you can see the world very differently. If the electrons are in front of the protons, then this is the only, so this will be the only way you can see a proton, would be at these angles, right? This angle and this angle, if the electron's in front. And if the electron's not in front, then you can see it straight on. So it's going to be a different world depending on where the electrons are and how stacked they are on top of the atomic surface. How many of these little electrons there are will also make a difference. So that would be part of the argument. You sort of have to understand that when you add electrons to a surface and charge it, they're like adding matter. They're gravitational in the sense that they're placing a weight, okay, that does push down on all the other electrons. So the more charge you build up, the more pressure you're creating inside, because all the electrons, the free electrons on the surface, aren't really free. I mean, they're not for free. They're weight on these other electrons. And that keeps increasing the voltage. So the more electrons you pile on, the higher and higher the voltage goes, the pressure of the average electron. All right, so when you're talking about moving it through a wire, what's the real deal? Is that you're saying the wire is balancing the pressure between all the electrons. So the conductor is saying, this is my natural state. And then you're introducing a jab into it. So it's like you introducing a jab into the ocean, I could argue. And I'll redraw the ocean crap, because it's essentially the same argument. Okay. Except you can go both ways. So what happens when you disturb the ocean is that you create you drop a rock into the water. You push the atoms into each other. What you're really doing is, compressing the electrons. So all the electrons and all the water molecules, let's just say the atoms, you're compressing the atoms. And so they want to go this way, but it's an uncompressible liquid, so you can't compress the actual atoms. You have to somehow displace them. Okay, so what happens is that this pressure against builds up immediately, because all these atoms say we're not getting any closer to each other. So you can't squish us, and you can't change our shape. You can't displace us, okay, without there being some place we can break free. So if we're not going to break free, if we're not going anywhere, we're full of water all the way to this shore over here. It's all water, okay? So there's nothing to compress here. There's no air bubbles to squish. There's nothing to squish. So the pressure, it hits a hard pressure right away, and it has to go either up or down, right? Because it can't go forward Where's the energy going to go? Well, it has to go this way, or it has to go that way. Now, obviously, down isn't going to work because the ground's in the way, and that's going to provide an up pressure. And so, obviously, it goes up into gravity. But the problem with going up into gravity is gravity's a rubber band, and the further up you go, the more pressure there is pushing you back down, so to speak. You have a constant force pushing on you down, and so you're going to end up going back down again, and then you're going to be faced with the same problem. You can't go back this way because that's where the high pressure started from, and that's where it's still going. And so you can't go forward because it's not incompressible, so you end up going back up again. So you end up with a wave. All right. So that's sort of happening with the electricity, in the sense you can understand that as you push on one electron, it's got to share, okay, that pressure with these other electrons. So what does it do? It does the same thing. It pushes it to the outside, but the outside doesn't work. Okay, it pushes. So the electron's pushing. It's adding pressure. The pressure is going both in this direction because it is compressible in a sense. All right, and it's leaking this way and that way. So as you push, the pressure is going to equalize into all the atoms eventually. But the idea is you're starting with a direction, and it's going to tend to go in that direction. So say if you have a very high voltage, a high pressure, you can hit just a few electrons and equalize your pressure between them and get to the finish line really quick. Or you can take a jerkier pattern and get there much later. And that's what you see as the voltage. The voltage starts off slow and then rises. Okay, it doesn't instantly pop to the, whatever voltage you put into a wire, it doesn't instantly create that voltage at the other end. Some of the electrons move quick, some of the electrons take a lot longer, because there's a whole bunch of pressure to be equalized. All right, and so what you're saying is you're putting this in, and then you're putting this in, you're putting this in. So you're putting a higher pressure in, and you've got to move the pressure of all these other electrons. Eventually, all of them will be that same pressure. So eventually you'll get them all up to that pressure, and then nothing's going to be changing in this wire, because all the action's going to be at this end, okay, where you have a small and it can leak out into work. All right, and this end there's still going to be some action, because yes, you're putting in a high pressure, and this one will always be a tiny bit lower than the pressure you're putting in, because this one's draining it out. So as long as this keeps draining it out, there's going to be, a difference, and this one's never going to be as high as the pressure you're putting in, because it's always leaking the pressure out. But they become a lot more average, and that's sort of the drift velocity. But the drift velocity isn't a meaningful concept. There's nothing drifting, because the electricity doesn't need to use all the atoms to get from point A to point B. So if you've got a high voltage, you use very few atoms. And the real giveaway is the fact that if you want to make magnetism, you need to involve a lot of atoms. You need a high amperage. So you need to be involving all the atoms in the process of moving the pressure. So you don't want a high voltage, you want a low voltage, and you want the pressure to spread a lot. So I guess the argument for that is you could sort of understand that if you did have something like friction, like the atmosphere, the faster you go, the more aggressive the pressure gets against you. Okay, and the slower you go, well, that's the opposite example actually. Let's see, let me think of a better example for the fact that going through maybe like clay or something, and the stickiness argument. So the faster you go through, the less you're going to tend to go in these other directions, all right, because you've put the energy in quickly. So you could argue that almost like speed of sound. Like if you get up to a fast enough speed, then the sound moves through the atmosphere much quicker, much more efficiently, with less friction than if you have it lower than that speed, because then the stickiness, okay, the fact that the other electrons are sticking to it is more effective. So it's like you're defeating the glue by going really fast. So the higher the pressure, the less spreading of the voltage, that is, the less friction. That's a good example. I should use friction as the example. The faster you go, the less friction with the other electrons. And the slower you go, the more likely it is the friction, okay, can affect you and drain your pressure. So if you go in with a low pressure, lots of atoms get involved. And if you go in with a high pressure, very few atoms get involved. That's sort of the base argument. But I mean, that's sort of a conclusion that can be drawn based on what the thing does, what the behavior is. And, you know, they don't talk about any of that stuff. So the real fact is that what I wanted to get to, I guess maybe I'll just redraw that, because that's obviously gotten cluttered. So I'll do that. So I just want to make the distinction between the electric and the magnetic, and the fact that what it is actually doing is changing the exterior of the wire. When you're putting electricity in, you're pushing the electrons essentially out. So the surface is becoming electrified, charged, and you're changing how it looks. And as that equalizes, that is, as the pressure equalizes throughout the conductor, then you can't see that difference anymore. But you can see the difference while you're turning electricity on and while you're turning electricity off, because then you can see the scale, the change in the size, the curved line. So that's why alternating current can be used as an inductor, because it is creating a changing magnetic field. And what it's really doing is initiating a magnetic field and then collapsing a magnetic field, and that is causing the other conductor to see that constant change and do the same thing. So if you can get the atoms in the wire to oscillate, you can get the atoms in the other wire to oscillate. All right, so another point to make, I mean, I want to kind of emphasize this idea of the pressure thing, so I think I can make this understood. So if you had these electrons, and the fact is they're sharing information about each other at the speed of light. So the force is reflecting between the electrons. So they're all aware of each other's pressure, so to speak. So if anybody's under less pressure somewhere, it's going to move into that less pressure, causing a spread of the less pressure, blah, 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 blah. So they're all kind of equalizing their pressure. So if I create a surface, all right, and again, the protons are locked in the atoms. There's no moving protons, okay? The protons are in the nucleus. They're kind of in a rigid position. They're not going anywhere. They're not doing anything. All you're really doing is changing the arrangement of the electrons to the protons. Gotta get some new crayons here. All right. Probably could do that. Wouldn't hurt either. All right, so if I had a surface and I start piling electrons on this outside, okay, which is adding electrons to the system, right? So they're going to tend to go to the outside because the inside is a constant amount of pressure, right? There's a constant amount of pressure on these electrons. Now, part of that is because of the external universe is constantly pushing, so that's part of the equation. You have to understand the external universe is constantly pushing. It's providing a constant amount of energy into the system. And this has to just equalize that energy. So it doesn't really matter, okay? So for every one I put another electron on here, I'm just adding another thing to collect the external pressure, right? So if I didn't have this one here, the pressure would have gotten collected down here somewhere inside the material. So it was going to get collected anyway. You're just collecting it at a different point, and that means you're going to be pushing from that outside. So the outside is always pushing in on any material object because the internal pressure is unlikely to be higher than the external pressure, right? It's equalized. It's at equilibrium in its pressure. And if you do anything to change the pressure inside, you're going to change the pressure on the outside by expanding it into that pressure. So if you move something into the pressure is going to eradicate that very quickly, and it's a constant pressure. So you can't really get rid of pressure by pushing electrons further out, because the external pressure is what's going to push them back in. You can't evade the external pressure, I guess is the point. So the electrons always have a mass pushing in. Yeah, that's one point. The magnetism one was the other point I wanted to make, so maybe I'll erase and do that one. Okay, so the sort of simple argument is you could argue that atoms have a shape, okay, and we'll say that it's sort of proportional, okay, in the sense that the electrons are proportionally balanced. And what you're basically doing is squishing the atom, right? So if you push on one electron over here, all right, you're going to basically be squishing the atom, which means these electrons are going to go out if you actually do succeed in pushing this one in. All right, and when you do that, you're maybe that's also going to cause this electron to move in. So basically the atom's shape changes from a non-polar shape to now a polar shape, where the electrons are very close here and they're very far here. So this is back to this argument, okay, that I can block something, okay, to a point. So the closer I bring this to you, the easier it is to disguise this thing behind it. I can make it just totally disappear. All right, and the closer they are to each other, the easier it is for this one to be seen. Okay, and that's sort of the trick here, is that you're changing how much you can see of the proton by, from different directions. So from this direction, the proton is easier to see than from this direction, where less angles are viewable to somebody looking over from over here. So the electron's blocking more of the proton here, and the electron's blocking less of the proton from these other two sides, and that's the polarization of north-south. Okay, well, this would be north-north, and this would be south here. And so that's the right-hand rule. That's the perpendicularity rule. Okay, so when you squish the atom, you're not creating a north-south, you're creating a south-south, or a north-north, depending on whether you've squished them this way or squished them that way. You're going to create a different polarization. And that's directional. All right, so I guess the point is the directionality would be caused by the fact that these electrons won't be moving straight this way. They're going to move this way. All right, so that's the technicality. So if I push the electron this way, I push these electrons that way and that way. So now we have a north here and a north here. All right. And then if you push the current the opposite way, then these electrons will be pushed this way and this way. So that's the difference, is you're pushing in a direction, and the direction just has to do with the fact that the electron isn't moving straight up and down, it's moving this way. Even though the force is perpendicular, the motion of the electron will be tangential to that perpendicular. Don't know if that's technically the right way to say it, but obviously it's good enough. I'm just saying there's a mechanics to it, okay, and some of this mechanics can be understood. Why there's a reason why direction matters, and there's a reason why something can detect the difference in the direction, because it's seeing it. So when something's looking at the wire, when it looks at it straight ahead, it's purple. When it looks at it this way, it's blue. When it looks at it that way, it's red. You can kind of get the idea. It's seeing it differently because there's a different pattern, but it's all the same force. It's just the force is in a different pattern because of the arrangement of the electrons and protons. All right, now we'll go back to the video.
To the right, but you also have a bunch of protons. So the net charge on this guy.
All right, so the protons really don't go anywhere. So again, this is just wrong to talk about protons moving. The nucleuses are really dense and heavy, and if you move them, then you're going to lose a lot of your force. So we know the force is fairly efficient through the wire, especially in a superconductor. We're basically putting force in and getting 100% of the force out. So to make any argument that you're moving nuclei around, I'd say it would be bullshit.
which will be the charge density of protons plus the charge density of electrons, is 0. Because there is an equal number of electrons and protons.
So there's no point in saying it, right? Because we know as you're creating the voltage in the wire, there's not an equal number. You're pushing electrons in. That's how you're creating a voltage. So why would you say there's an equal number of protons and electrons? You know you're adding electrons. That's the pressure. I mean, even if it's an alternating current, you're adding it and then you're subtracting it. Then you're adding it and then you're subtracting it. You're always adding something to create the higher pressure. You can't create the higher pressure without moving the electron. So there's obviously technically more electron in the wire. When you push just one electron in there, you've created more pressure in that whole wire. Because again, it's like an uncompressible liquid.
A proton moves a little bit away from the electrons, and somehow there's a little bit of positive charge somewhere on this wire. Electrons, which are moving with the current, will also immediately move isotropically to neutralize.
So it doesn't happen. So she's saying they're moving isotropically. They're not moving. The nucleuses are totally out of this game altogether, I would argue. I'd argue there's just no evidence that nucleuses are playing any role at all because of the efficiency with which you're transmitting the pressure. You couldn't transmit the pressure efficiently if you were jiggling a nuclei. That would absorb a lot of energy. That would be very hot. That would be a lot of things. So that you can't be doing that. You're just pushing on electrons.
Is that charge. So the net charge on this is 0. And I should also mention that this velocity here is on the order of millimeters per second. It's pretty slow.
So again, that's what their assumption is that every single electron is being moved in the wire. And so you're taking the speed and dividing it over every single electron. When no, the argument is that the pressure is moving fairly efficiently through the shortest path, so to speak. And you don't need to move every single electron every single time. You just need to move the ones that get you to the place where the electrons are being pulled away. So the place where the electrons are being removed is the place you're going to. And those two lines, the removal of electrons and the ones where you're adding electrons, those two lines want to connect. And they don't need to move every single atom in the conductor. Now, if you use a low voltage, and a high amperage, then you will use more of the atoms. And that means that's the whole point of me talking about the magnetism thing. When you're changing the shape of a whole bunch of atoms, then you're creating a bunch of little magnets inside of the wire. And so the more atoms you misshapen, the more magnetism you can create.
Which is interesting. Well, I mean, that's not slow, but when you imagine a circuit and you're like flicking on a light switch, the light immediately comes on.
Now, so it doesn't. So we already, so why say it? We know it gradually, the voltage arrives gradually. There's one electron that gets there really quick, and then there's a few others that get there fairly fast, and some others get there after that. But you know that it gradually builds up. It doesn't just instantaneously go from off to on. That doesn't happen. It doesn't go from 0 watts to 500 watts. It doesn't do that. It slowly increases the wattage. The amount, the volume of electricity takes a while before you've filled the entire conductor. Okay, now the whole conductor is now at the right voltage, and now you can pump it in. So if you have the switch really close to the light bulb, that's better. Okay, it's more likely to be a very fast reaction, but then you still have to go through the switch, and the switch is going to be imperfect. So, but it's wrong to say it happens instantaneously, because it does happen at the speed of force minus the slowness of the speed of the electrons. The electrons obviously are carrying the force, and when they're carrying the force, it's going less than the speed of light.
Right? You don't expect to have to wait millimeters per second while the electrons move through your ceiling. This was explained to me as like thinking of circuits as like, imagine water pipes full of marbles, and the marbles are electrons.
Right, and so if you did do that, you would imagine that a bunch of the marbles don't move. I have a big pipe, and I push on one marble really fast that I could end up sending that signal through a pathway of marbles, and I never hit the ones on the outside at all. They don't even move. They don't jiggle. They don't do anything. They don't even know that I moved a bunch of marbles.
Right. The group velocity of those marbles is some speed, millimeters per second. But if you flick a light switch, you essentially like open a gate that allows more marbles to come through. So on the other end of the pipe, just immediately after you open that switch, marbles can pop out.
So again, they can, and very few do. So that's the whole argument, is that it's not about the group, as you say. The group needs to be, you need to use some of the electricity again to get the whole wire equalized to that pressure, and that takes some time before the rest of them now can move very fast, because they don't have to equalize the pressure with all the ones that are stealing a little bit of friction. And it's hard to call it friction, right? Because you already know that if it pushes up into gravity, it's going to get pushed back down again. So you're going to get the pressure back, all right? But you are losing it in terms of time. It takes time to push it up, and it takes time to push it down. You're not losing any pressure, but you are losing a little bit of time.
Because they're all being pushed through. And that's what's happening. It's not that you have these incredibly fast electrons.
Yeah, you do. You have very fast ones and very slow ones. It's the path. The path can be like lightning. It can be fairly straight. You know, you can have some lightning bolts that go pretty straight, and then a little crook, and then it's pretty straight and crook, and one crook. Then you can have lightning has 7,000 crooks in it. So obviously it's not the same path, it's not the same speed. This stuff isn't moving the same exact speed because obviously it takes more time to move the matter. The matter's slower. So some of the electricity gets it through really quick, and some of it lags behind.
Moving at the same, well, they are going fast, but the group velocity is not that fast.
So there is no such thing as the group velocity or the drift speed. These are not rational concepts that actually take place in the wire. The wire doesn't have anything called a drift velocity, because even when you pressurize the whole wire, I could still hit marbles in the middle, and the outside marbles aren't going to know anything about it.
It's on the order of millimeters per second. Okay, so in addition to our current carrying wire, we are going to have a positive charge Q that is some distance r from the wire, and it will also be moving at the exact same velocity v in the same direction.
So the same velocity v. What velocity? What are you talking about a velocity? So is that the drift velocity, or is that the voltage? What are you talking about? So what is he talking about? What does velocity mean in this context? I mean, velocity could only mean to me voltage. You're talking about the voltage, right? I don't know. What else is velocity? What are you talking about? Are you actually talking about the drift velocity? So it's moving the same speed as the drift velocity? Which, again, isn't a real phenomenon. There's no such thing as, there's no drift velocity moving through the wire. There's no thing that moves at the speed of the drift velocity. There's nothing moving at that speed. So it doesn't even mean anything. All right, and then she's going to call this has something to do with magnetism, when a single charge isn't a dipole, so it can't see magnetism. So it's not going to react to magnetism.
To the right. The question I want to ask is, what is the force on charge Q? What is going to happen to charge Q as a result of being next to this current carrying wire? So now
So now she gets into the whole math thing, and this has to do with, you know, understanding the difference between lines of force. That is, every charge is radiating straight lines out of it. So the red thing has got a bunch of red lines, the blue thing's got a bunch of blue lines. These are lines of force. That's how much charge it has, is how many of those lines you cross. The closer you get, the more lines you cross, the more force there is. That kind of idea. And field lines. Field lines are an emergent byproduct of the lines of force. Nothing travels a field line. It's a completely artificial mechanism. There's no such thing as a field line. It's completely created by whatever substances you've made to fill that void, the magnets. The iron filings create a new magnet with the opposite polarity of the original magnets. The original magnet's north-south. The iron filings line up south-north, south-north, south-north. So they're all repelling each other. That's why there's separation between the lines, is because they're opposite, they're same polarized magnets, and they're basically saying I can't be closer to that guy over there. So they're basically building a magnet in space, and the magnets are staying separated because they're the same polarization. So they're repelling. There's no line. Okay, they line up that way based on the pressure created by the field force lines, the lines of force. The lines of force are telling them how much pressure there is at all these locations, and there's equal potential. And where there's an equal potential is where those little iron filings are lining up. But that line is not a line of anything. Nothing's traveling that line. Anyway, so much of their physics is just such junk. Alright, so I don't think she says anything here. She just goes into the stupid math.
If you would like to solve the problem yourself, pause right here. The answer will be at this time.
Right, so who cares, right? So this is just the generic, doing some Maxwellian math, do your little right-hand rule-y stuff, all that kind of crapola. Don't actually find the exact number of anything. Don't put real numbers in and show us that it actually happens. Just reduce an equation that's this big into an equation that's this big, and that's all they do. And then they put a box around it and say that's an answer. When, yeah, obviously it's not much of an answer. All right. So I think we'll call that a video. Ooh, 51 minutes. Didn't think it would take that long. But anyway, it is what it is. So, I just, physics is just so bad. All these characters. And the sad fact is people fall for this crap. People fell for the silly Jesus stories. I mean, it's in spite of how miserable their life is, their kids dying, their wife dying in childbirth, all kinds of just horrible. You can't even imagine how horrible it is. The plague, all kinds of crap. I mean, all the little miseries, all the big miseries. I mean, even as a woman, believing that God cursed me, okay, because Eve gave Adam an apple, and for eternity I have to have this stupid, curse. I can't cut a break. I can't have a baby easily. I have to have a baby hard. Because Eve pissed God off, and he's got to get revenge against me. And people fall for that crap. And you're saying, gee, well, yeah, so obviously they'll fall for anything. But why do they believe these people? Why do they believe these silly stories? No details, no mechanisms, no pictures, really nothing. They simulate nothing. They just draw these silly things. This thing is flying through space. This little wavy line is flying through space. How does it know how to wavy? How does it know how to do any of that crap? It's just so bad. Ugh. I hate this planet. I just didn't anticipate that people were belligerently stupid. They're not just stupid, okay? They're really trying to stay stupid. Because I can't be this alien. I mean, how can they be so impervious to a little bit of logic? And, just to reject logic just out of belligerence. It's hard to understand. I'm clearly not one of you. Anyway, till the next time and such, so forth and whatnot.